let's start the unit on curve sketching in the calculus course. So the first lesson, we're going to look at how can we tell if a function is increasing or decreasing based on the value of its derivative. And we'll also touch on things called critical points. Now, the first thing we should establish is what does increasing and decreasing mean? Well, I have the definitions below here for you. Increasing means as x values increase, the y values are also increasing. If a function is decreasing, that would mean as the x values are going up, the y values are going down. So let's go through this investigation I have at the beginning of the lesson here. I have the graph of a function in red and its derivative in blue. So the red function is f of x, the blue function is f prime of x. And I've also put these graphs into Desmos, and I have Desmos telling us the value of the function at a given x value and the value of the derivative at that same x value. And I'm controlling the x values up here. And I have Desmos showing us the slope of the original function at the x values by having it draw in the tangent line. Remember, the tangent line, the green line there, is a representation of the slope of the original function. And the value of the derivative tells us the slope of the tangent, which means it tells us the slope of the original function. So for example, let's say when x is -2, I see that the value of the derivative is -3. That's why on the graph of the derivative of the blue function, there's the point -2, -3, because when x is -2, the value of the derivative is -3. Now, what does that tell us about the original function? It tells us when x is -2, the slope of the original function is -3, and that slope can be represented using this tangent line. So basically, the slope of this green line, which represents the slope of the red function, is -3. Now that you hopefully remember the connection between the value of a derivative and how it tells you the slope of the original function, which can be represented with the tangent line, let's answer some questions. Part A says, over which values of x is f of x increasing? So looking at the red function, when is this red function increasing? So in other words, when is the red function going up to the right? The red function is increasing in this section, and then again in this section. Those are the two sections where the function is going up to the right. Those are the two sections that as x is increasing, the y values are also increasing. So when x is less than -3, and then when x is bigger than 1. So let's write down those two intervals. So when is f of x increasing? When x is less than -3, or when x is bigger than 1. And we could write it like that using inequalities, or we could write it in interval notation and say when x is an element of numbers between -∞ and -3, or from 1 to infinity. Two ways of writing the same information. Over which values of x is f of x decreasing? The red function is decreasing, going down to the right over this section right here, which I have highlighted. So that would be between x values of -3 and 1. The red function is decreasing in that interval. So we could write it as an inequality, x values between -3 and 1, or an interval notation saying x is an element of numbers between -3 and 1. Either way is fine. Now here's the important part. What's true about the graph of f prime of x, the derivative, when f of x is increasing? Remember, the derivative tells us the slope of the original function. If the original function is increasing, so let's look when f of x is increasing. Actually, let me go over to Desmos for this. Okay, so the red function, f of x, it's increasing when x is less than -3. What do you notice about the value of the derivative in that section? And remember, the value of the derivative is being shown to you right here. That value represents the slope of the red function, which can be represented with a tangent line. So the value of the derivative is telling us the slope of the tangent at any point on the original function. Notice, what are all those values in this interval for x values less than -3? All those values are positive. That's why the graph of the derivative in that same interval is above the x-axis. All its y values are positive because the y values tell us what the tangent slope, or the slope of the original function, is at any given x value. So the fact that when x is -4, I see that on the graph of the derivative, the y value is 5, that tells me on the original function when x is -4, if I were to draw a tangent line to the original function at that point, the slope of that tangent line would be 5. So the y value of the derivative tells us the slope of the original function at any x value, and the slope of that function can be represented using a tangent line. And look at the other interval where f at x is increasing, so for x values bigger than 1, notice in that section, where's the derivative? The derivative, once again, in that section is above the x-axis. And remember, the y values of the derivative tell us the slope of the original function, which can be represented with this tangent line. Look at the value of the derivative in this interval. It's always positive. So what's true about the graph of f prime of x when f at x is increasing? When f at x is increasing, the graph of f prime of x is above the x-axis. It's always positive. So f prime of x is greater than 0. So when f at x is increasing, the derivative is positive. Okay, and what's true about the graph of f prime of x when f at x is decreasing? Well, f at x is decreasing between x values of -3 here and 1 here. Between those two x values, the original function is going down to the right, which means it has a negative slope, which is why if you look at the value of the derivative at any x value in that interval, the value of the derivative is negative. And the actual graph of the derivative is below the x-axis. It has negative y values because the y values at any given x value tell you the slope of the original function at that given x value. So on the derivative, when x is -2, I see a y value of -3. What does that tell us about the original function? It tells us at an x value of -2, the slope of the original function is -3. And that slope can be represented using this tangent line. So the slope of that tangent line is -3. So the value of the derivative tells us the slope of the original function at any point. So what's true about f prime of x when f at x is decreasing? Well, if f at x is decreasing, it's going down to the right, which means it has negative slope, so that's why the derivative would have negative values. It would be less than 0. So let's write our conclusion here. Effects of f prime of x on f at x. When the graph of f prime of x is positive or above the x-axis on an interval, that tells us that the original function is increasing over that interval. And if the value of the derivative is negative, well, that tells us the slope of the original function is negative, which means the function must be decreasing over that interval. So here it is summarized for you here. If f prime of x is positive, f at x is increasing, and if f prime of x is negative, f at x is decreasing. Now we're going to pay special attention to things called critical numbers. Let's look at this definition here. A critical number is a value of a in the domain where f prime of a is either 0 or undefined, meaning f prime of a doesn't exist. So a key thing here is a has to be in the domain of the original function, and if that value of a makes the derivative be 0 or undefined, we call that value of a critical number. Critical numbers are important because they could yield a few different things. They could indicate that there is a local max, a local min, or neither on the original function. And let me show you why. Well, let's look back to the original example. Notice, when was the derivative 0? It was 0 at -3 and at 1. And what's true about the original function at those points? Well, that must mean the original function has a slope of 0 at those points, which is represented with a horizontal tangent line. And notice, wherever there's a horizontal tangent line, there's a turning point. So this turning point at an x value of -3 was a local max, and this turning point down here when x is 1 was a local min. Now, a value of 0 for the derivative doesn't necessarily mean there's a local max or min. I'll teach you how to tell, but it indicates that there could be a local max or min there, which is why we call it a critical point. Here are the scenarios. So when is a critical number a local max? So I have a function f at x here, and I have a box around this section I want you to pay attention to where there is a local max on the original function f at x. What would be true about the derivative at that value of x and before and after that value of x? Okay, let's pay attention to this local max point up here. The x value is like 2.1-ish. At that point, there would be a horizontal tangent line. I don't know if I'll be able to get it to give it to us exactly, but you can notice at that point, the tangent line would be horizontal, which is why if we look at the derivative, which tells us the slope of the original function at that x value, we would see a y value of 0 on the derivative, because the y value of the derivative tells us the slope of the original function at that x value. But what I'm interested in is, what was the value of the derivative before that x value? It looks like the derivative was positive, which means the function was increasing before. And then what's the value of the derivative after that x value? The value of the derivative is negative, which means the function is now decreasing. So the function was increasing before the critical number, decreasing after the critical number, which means it must be a local max point. And if we look at the derivative, we can tell that it was increasing before, because if we look at the y value of the derivative before that x value of 2.115, the derivative is positive. Right there it's 0.687. And then after, the derivative is negative. Here it's negative 0.605. And remember, when a derivative is positive, it tells us the function is increasing. And when a derivative is negative, it tells us the original function is decreasing. So looking here, I can tell that before the x value of 2.115, that critical number, I know the function was increasing. And then after the x value of 2.115, the original function was decreasing. And if we look at the original function, yeah, we can see that. It was increasing before, decreasing after, which means it was a local max point. I just have that outlined here for you. There's a local max here, and we can tell because the derivative switches from being positive to negative around that critical number, which means the original function went from increasing to decreasing. So it must be a local max point. So let's comment on how we can tell if there's a local max from the derivative. So I can tell there's a local max if, first of all, the derivative is 0 at an x value, and before that x value, the derivative is positive, and after it is negative. So there's a local max if the derivative is 0 at the point, and the derivative switches from positive to negative around that x value. Because if the derivative switches from positive to negative, that means the original function went from increasing to decreasing, which means the place where the derivative is 0, where it has a horizontal tangent, must be a local max. Okay, what would indicate there's a local min? Well, notice at this point here, there's a local min. And that's because before the x value of this point, the function is decreasing, and after, the function is increasing. So when that happens, you have a local min. And since the function is decreasing before this x value of like negative 1.5, I know if I were to look at the graph of the derivative, it would have negative y values in that section. And yes, it sure does. And after the x value of negative 1.5, the function is increasing, which means the derivative, which tells us the slope of the original function, will have positive y values in that section. And at this point, there's of course a horizontal tangent, which means the function has a slope of 0 there, which is why the derivative has a y value of 0 there. So we can tell there is a local min point on an original function if the derivative is 0 and switches from being negative to positive. Now the next example I wanted to put in here is to just show you that just because the value of the derivative is 0 doesn't necessarily mean there is a local max or min. If we look at this point right here on the function, that is not a local max or a min. But the value of the derivative there is 0. If we look at the graph of the derivative, at an x value of 0, the y value is 0. That means on the original function at an x value of 0, there would be a horizontal tangent there. The slope of the original function is 0 there. But before that x value, the function is increasing, and after that x value, the function is increasing, which means the derivative is going to have positive y values before and after. Since the value of the derivative is not changing signs, we know it is not a max or a min function because the original function is not changing between increasing and decreasing. It's increasing over that entire interval. So we say it is neither a local max or a min if f prime of x equals 0, but does not switch signs. And let me just switch over to Desmos. Notice at the x value of 0, the original function, its slope is 0, indicated by the slope of that tangent line. It's a horizontal tangent line, slope of 0, which means the value of the derivative is 0 there. So here's the derivative, the y value is 0 there. But before the x value of 0, the original function was increasing, indicated by this positive derivative value. And after an x value of 0, the function is still increasing, indicated by this positive derivative value. So the derivative is positive before and after, right? It's positive here, which means that the original function never switches between increasing and decreasing. So at an x value of 0, it's not a local max or min. Now I told you critical numbers are x values that make the derivative be 0 or undefined. So far we've just looked at examples where the derivative is 0. How about undefined? Let's look at this one. There could be something called a cusp on a function. And this function, let me just show it to you in Desmos. It clearly has a local min point at the origin there, 0, 0. But what's the value of the derivative at that point? Well, let's look at the slope of the function around that point. So the slope of the original function is represented with that green tangent line, and the value of the derivative tells us that slope. It's negative 0.88 right here. And then as I get closer to that cusp, that tangent line looks like it's getting more vertical, right? It's getting really, if I could get right into that cusp there, the tangent slope would be perfectly vertical. And what's the slope of a vertical line? It's undefined. The value of the derivative there is undefined. This is just an example about how an x value that makes the derivative be undefined could indicate to you that we have a local max or min in the form of a cusp. So if we look here, the value of the derivative right there would be undefined. And I can tell that by looking at the graph of the derivative. Notice there's a vertical asymptote there. The derivative doesn't exist there. It's undefined there because it would have a perfectly vertical slope there. But before that cusp, the original function was going down to the right, and after, the original function was going up to the right. So there is a switch. It was decreasing before and increasing after. And look at the graph of the derivative. Negative y values before, positive y values after, which tells us decreasing before, increasing after. And if we look here, look at the value of the derivative before, negative, the value of the derivative after, positive. So that means it was decreasing before, increasing after, which means there must be a local min at that point. So another thing that could happen, we could have a local min if f prime of x does not exist and switches from negative before to positive after. Switches from negative to positive, right? Because that means it went from decreasing to increasing. Oh, and I know it's not in your lesson, but I just wanted to show you an example of how an undefined slope could not be a cusp, how it could not be a local max or a min. And I just put an example in here. Notice this red function, at an x value of 2, the derivative doesn't exist, and that's because the slope of it is perfectly vertical. We can tell by the tangent line it's approaching perfectly vertical, but that point right there is not a local max or a min point. So just because we have an x value that makes the derivative be undefined doesn't mean it's a local max or a min. We'd have to test. Notice the function was increasing before. I can tell that by the positive derivative value, and increasing after. I can tell by the positive derivative value. So there was no switch from increasing to decreasing. So it's not a local max or min. So our conclusion, local extrema occur when the sign of the derivative changes. If the sign of the derivative does not change, there is no local extrema, so no local max or min point. A critical number of a function is a value of a in the domain of the function where either f prime of a equals 0 or f prime of a does not exist. That's the definition of a critical number. We already talked about that. If a is a critical number, then at a f at a, we have a critical point. And the critical point could be a local extrema, but not necessarily. We have to test the value of the derivative around the critical number to see if the derivative changes signs. And that whole process is called the first derivative test. And in the next example, we'll be applying the first derivative test to check and see if critical points are local max or min points. Example 1 says, determine all local extrema for the function below using critical numbers and the first derivative test. It also asks us to state when the function is increasing or decreasing. So you have to remember that a critical number is a x value of the function that's in its domain that would make its derivative be either 0 or undefined. So in order to find the critical numbers, I'm going to first have to start by finding the derivative of this function. So f prime of x equals, and I just need to use the power rule to get 6x squared minus 18x minus 24. That's the derivative. This tells us the slope of the original function at any point we want. We're interested, when is this 0 or undefined? Well, this is a quadratic. It can't be undefined. It's a continuous function. But it could be 0. Let's solve for that. And to figure out when this could be 0, I need to get it into factored form. Let me actually common factor out a 6 first. That would make this easier. So I'd have x squared minus 3x minus 4. And then in brackets there, the numbers that multiply to -4 and add to -3 are -4 and 1. So the solution to this equation would be either 4 or -1. So there's two solutions to that. So we have two critical numbers. The critical numbers are -1 and 4. Critical points would be, okay, well, what is the coordinates of the points on the original function at those x values? So I need to plug those x values into the original function and see what the y values are. So we'll plug -1 into the original function and 4 into the original function, and we'll get the y coordinate that goes along with each of them. So I've actually got Desmos to help me out here. So we figured out -1 and 4 were the critical numbers. Those were the numbers that if we look at the value of the derivative is 0 there. The slope of the function is 0. And the slope is represented by a tangent line, and we can see the horizontal tangent, which means it has a slope of 0. So at -1, the value of the derivative is 0, but what's the value of the original function? The value of the original function is 3. So this point right here, the point -1, 3, is a critical point. And where's the function when x is 4? Well, I know when x is 4, there's a horizontal tangent there, yeah, but what's the y value of this point? -122, and I get that by plugging into the original function. I get -122. Now let's do the first derivative test. The first derivative test is going to tell us whether these critical points are local max, min, or neither. Now we already saw the graph, so we know what they are, but how could we tell using the first derivative test? So this table is what we're going to use for the first derivative test. What we need to do is we need to check what is the value of the first derivative around these critical numbers. So in the first derivative test, we always put -infinity and +infinity on the ends. And then in between are the critical numbers in ascending order, so -1 and 4. So I know at those x values, the value of the first derivative is 0. But what's the value of the first derivative before an x value of -1? Well, let's pick a test point in here. How about -2? What's the value of the first derivative? Well, if I look at this graph, here's the graph of the function. Before an x value of -1, notice that the function is increasing, which means the first derivative should have a positive value. And if we plug in -2, notice the value of the first derivative is 36. And we can get that by plugging -2 into the equation of the derivative right here. Either that version or the factored version, doesn't matter. If we plug -2 in, 6 times -6 times -1, that gives us 36, which is positive. What does that tell us about the original function? Since the first derivative is positive in the interval from -infinity to -1, that tells us the original function has a positive slope, which means it is increasing. So f of x over that interval is increasing, means it's going up to the right. How about between -1 and 4? Between those critical numbers, let's pick an x value. How about 0? What's the value of the derivative at an x value of 0? Well, if we look at the graph, at an x value of 0 here, the original function is clearly going down to the right. It's decreasing, which is why the first derivative has a negative value. And we can get that negative value, -24, by plugging 0 into the equation of the derivative. 6 times -4 times 1 is -24, so it's negative, which means the original function is decreasing. So it's going down to the right. Okay, so notice before an x value of -1, the function was increasing. After an x value of -1, the function is decreasing, which means at -1, there must be a local max. So local max at the point -1, 3. At -1, 3. Okay, and then what happens after the critical number of 4? So between 4 and infinity, let's choose 5. If we plug that into the derivative, if I plug 5 into the derivative, I should get a positive number. I can tell that because the original function is increasing. The tangent slope is going up to the right. And what is the slope of the original function? It is 36. And we can get that by plugging 5 into the value of the derivative, either factored or standard form. I have 6 times 1 times 6. That's 36, which is positive. So that means the original function is increasing, which means at 4, since the function was decreasing before, had a slope of 0 at 4, and then was increasing after, we know that it was a local min. local min at the point for negative 122. And then what I also want you to notice is how we could use the graph of the derivative to verify this. So if I graphed the derivative, which tells us the slopes of the original function at any point, notice at negative 1, the value of the derivative is 0. Before an x value of negative 1, the derivative is up here, positive, which means the original function is increasing. And after an x value of negative 1, the derivative is negative, which means the original function is decreasing. So the derivative switches from positive to negative, which means it was a local max. And at an x value of 4, the derivative switches from being negative to positive, which means that the original function went from decreasing to increasing, which means a local min. Example 2. For each function, use the graph of f prime of x, so the derivative, to sketch a possible function f at x. So for this one, the derivative is degree 0. And an important relationship between a function and its derivative to note would be that the original function will have to be 1 degree higher than its derivative. So f prime of x is degree 0. Therefore, f at x is degree 1. So we're going to have a linear function. Now, what do we know about this derivative? This derivative, its y values are always negative 2. It's never changing. So f prime of x is always negative. And remember, the sign of the derivative tells us whether the original function is increasing or decreasing. Therefore, f at x is always decreasing. So we need to draw a function that is always decreasing. And I could be a little more specific. It's always decreasing at a rate of negative 2, because that's the value of the derivative. It's always negative 2. And the value of the derivative tells us the slope of the original function. So I need to draw some linear function that has a slope of negative 2. And it doesn't matter where the y-intercept goes. I'll just put it right here. Slope of negative 2. I'll plot a couple more points. And I'll draw a line through this. And there is a possible graph of f at x. Notice the slope of that function is always negative 2, which is why its derivative always has a value of negative 2. The derivative is always negative, which is why the original function is always decreasing. In part B, I can tell the derivative is degree 1. It's a linear function. Therefore, the original function must have been degree 2. It must have been 1 degree higher. So our original function is a quadratic function. It's going to be a parabola shape. Let's get the correct intervals of increasing and decreasing based on the graph of the derivative. So when is the derivative positive? The derivative appears to be positive at all x values less than 2. When x is less than 2, the derivative is above the x-axis. So I'll write the derivative is positive, greater than 0, when x is less than 2. And that means that the original function must be increasing over that same interval. When is the derivative negative? It's negative for x values greater than 2. Notice when x is greater than 2, the derivative is below the x-axis. What does this tell us about the original function over that interval? It tells us that the original function is decreasing. A negative derivative value tells you the original function is decreasing. So before an x value of 2, the original function is increasing. After an x value of 2, the original function is decreasing. What's happening at an x value of 2? Well, if we look at the derivative, notice the derivative is 0 at an x value of 2. So f prime at 2 equals 0. And since the derivative was positive before and negative after, we know that the original function was increasing before and decreasing after, meaning at the x value of 2, at that critical number 2, there's going to be a local maximum point. Now, I don't know exactly the y-coordinate of that local max. It could be here, could be here, could be here, doesn't matter. I'll just put it right here. But I know that's going to be a local max. I know the original function is going to be increasing before an x value of 2 and decreasing after an x value of 2. So there we go. There's our graph of f at x. Part C. So this function, the derivative, is degree 2. I can tell that because it's a quadratic. Therefore, f at x must be degree 3. Now let's look at the intervals of when this function is positive and negative. F prime of x is greater than 0 when x is less than 2 or x is greater than 2. For an x value less than 2 or greater than 2, the derivative would be positive. It's above the x-axis before 2 and after 2, which means the original function, f at x, is increasing when x is less than 2 or when x is greater than 2. What's happening at 2? F prime at 2 is 0. That means that 2 is a critical number, which could be a local max or a min. But because the function is increasing before 2 and after 2, there's no switch between increasing or decreasing, so it's not a max or min. F prime of x does not change signs, so there is no local max or min at the point 2 f at 2. But I know at an x value of 2, the original function has to have a slope of 0. It's just the function has to be increasing before and increasing after. So what's that going to look like? So let me just put a point somewhere when x is 2. How about here? Before that point, the function has to be increasing, and after that point, the function has to be increasing. But at that point, I need to have a horizontal tangent slope. So the function has to go completely horizontal at that point. So it would look something like this. It would do like this S shape through that. So it gets horizontal just at that point and then continues to increase after. So this function increases before that point and increases after, which is why the derivative is positive before an x value of 2 and positive after an x value of 2. The next one, and this is our last one. Once again, our derivative is degree 2. F prime of x is degree 2. That tells us that f at x must have been degree 3. Okay, let's write down when the derivative is positive. F prime of x is greater than 0 when x is less than 1 or x is greater than 5. That's when the derivative is above the x-axis. So that tells us the original function must have positive slopes in those intervals. So the original function must be increasing in those same intervals. So f at x is increasing over that same interval. So when x is less than 1 or x is greater than 5. The derivative is negative, so f prime of x is less than 0 when x is between 1 and 5. That's when the derivative is beneath the x-axis. That means the original function must have negative slopes in that interval, which means it must be decreasing. And notice the value of the derivative at an x value of 1 is 0, so that's a critical number. And f prime at 5 is also 0, so that's a critical number. Now, are those critical numbers going to result in local max or min points on the original function? Well, at an x value of 1, the derivative was positive before and negative after, which means the original function was increasing before and decreasing after. So it went from increasing to decreasing, which means there must be a local max. Local max at the point 1, f at 1. And I should write that in blue because I'm talking about the original function. So there's going to be a local max somewhere at an x value of 1. I'll just put it here. And how about at an x value of 5? Well, the derivative was negative before and positive after. So before 5, that means the original function was decreasing. Then after 5, it was increasing. That means it was a local min. At the point 5, f at 5. So there needs to be a local min somewhere when x is 5. Doesn't matter where. It could be up here, down here, wherever. It just has to be below wherever that local max was. So I'll put it down here. So if we read our intervals of increasing and decreasing, I see that f at x was increasing before 1. It was decreasing between 1 and 5. And then it was increasing after 5. There we go. This is f at x. Almost done. Example 3, sketch a continuous function for each set of conditions. So f prime of x is greater than 0 when x is less than 0. So when you see the derivative being greater than 0, that means the original function is increasing over that interval. So I can write down f at x is increasing when x is less than 0. And I know that because the derivative is positive over that interval. And the derivative is negative when x is greater than 0, which means the original function is decreasing when x is greater than 0. And it tells us f at 0 equals 4. So there's a 0.04. And I know my function, so I'm going to be graphing function f at x. I know this function is increasing before 0 and decreasing after. So we've got increasing before, decreasing after. So it looks like a quadratic. And we could make a note, there is a local max at 0, 4. And I know that because the function was increasing before and decreasing after means local max. Part B. The derivative is positive when x is less than -1 and when x is greater than 2, which means the original function, f at x, must be increasing over those two intervals. F prime of x is less than 0, so negative, between x values of -1 and 2. That means the original function is decreasing over that interval, and it gives us a 0.00. So I need to draw a function that is increasing before -1, and then decreasing between -1 and 2, and then increasing greater than 2. So because it's increasing before -1 and then decreasing after -1, there must be a local max at -1. So I'll jot that down, local max at -1, f at -1, wherever that is. And then what happens at 2? Well, before 2, the function was decreasing, and after an x value of 2, the function is increasing, which means there must be a local min at an x value of 2. Local min at 2, f at 2. So at -1 and then some y value, there's going to be a local max. So I'll just put it up here, why not? And then at 2, f at 2, wherever that is, there's going to be a local min. I'll put it here. And let me draw the correct intervals of increasing and decreasing. So I need to increase before -1, decrease between -1 and 2, making sure I go through that point it gave me, and then increasing after 2. Now this function could take lots of different shapes, but it has to have the correct intervals of increasing and decreasing with local max or mins at the correct x values, not necessarily the correct y values. There's lots of functions that would meet the criteria of the question. Last example, example 4. The temperature of a person with a certain strain of flu can be modeled by this function, t at d equals, where d has to be between 0 and 6, and d represents the number of days after a person first shows symptoms, and t represents their temperature in degrees Celsius. During what interval will the person's temperature be increasing? So that means when is the slope of the function going up to the right? When is the slope of the function positive? The slope of the function will be positive whenever the value of its derivative is positive. So let's find the derivative and figure out, well, when's the derivative positive? So let's start off by finding the derivative. T prime at d. So I would get -10 over 18d plus 15 over 9. That's the derivative. Let's figure out a critical number, because a critical number is a place where the function might switch from increasing to decreasing or vice versa, right? It might be a local max or a min. That'll be our dividing point from where we test around to see when the function is increasing or decreasing. So a critical number would be a number that makes this be 0 or undefined, and this is just a linear function, so it can't be undefined, but it could be 0. So let's set this to 0 and solve. I'm going to multiply both sides of this by 18 just to get rid of the fractions. So I'd have 0 equals -10d, and then multiply this term by 18 as well. 18 over 9 is 2, 2 times 15 is 30. If I solve this for d, I'd have -30 equals -10 d, divide both sides by -10, I get d equals 3. So that tells me at 3 days, the slope of the function is 0, which means that might be when the temperature is at its highest in this scenario, or when the temperature is at its lowest, or maybe the temperature is always increasing or always decreasing. I don't know what we have, but what I'm interested in is when is the temperature going up? So I know if I make the table for the first derivative test, that will tell me the intervals over when the function is increasing and decreasing. So I put -infinity and infinity across the top and put the critical number here. I'll calculate what's the sign of the derivative in each interval, and what does that tell me about the original function. So let's pick some values. So keeping in mind I have to stay within the interval from 0 to 6, so I'll pick 2 and 4. What's the value of the derivative when x is 2? Well, here's the derivative. If I plugged 2 into this equation, I'll just do this off to the side. T prime at 2 would equal -20 over 18 plus 30 over 18. That's 10 over 18, that's positive, which tells me the original function is increasing. So the temperature must be increasing over that interval. How about when d is 4? I'd have -40 over 18 plus 30 over 18. That's -10 over 18. That's negative, which means the temperature must be decreasing over that interval. So at day 3, that's when the temperature would be at its max. But before day 3, the temperature would be increasing. After day 3, the temperature would be decreasing. And the question just says, during what interval will the person's temperature be increasing? So we could say the temperature will be increasing between 0 and 3 days. Okay, that's it.